Today we will discuss about the atmospheric stability. Introduction. Atmospheric stability is a fundamental concept in meteorology and climatology. It determines whether an air parcel will rise, sink, or remain at its original position after being displaced. Stability plays a crucial role in cloud formation, precipitation, and weather patterns, making it an essential topic for competitive exams like CSIR NET. What is atmospheric stability? Atmospheric stability refers to the resistance of the atmosphere to vertical motion. It depends on the temperature difference between an air parcel and its surroundings. If a displaced air parcel returns to its original position, the atmosphere is stable. If a displaced air parcel continues to rise, the atmosphere is unstable. If the air parcel remains in equilibrium, the atmosphere is neutral. Lapse rate and its types. What is lapse rate? Lapse rate is the rate at which temperature changes with altitude in the atmosphere. It is a key factor in determining stability. Types of lapse rates. 1. Environmental lapse rate, ELR. The actual rate of temperature decrease with height in the atmosphere. Varies with time, location, and weather conditions. 2. Dry adiabatic lapse rate, DLR. The rate at which unsaturated air cools as it rises or warms as it sinks. Fixed at 10 degrees Celsius per kilometer. 3. Moist adiabatic lapse rate, MELR. The rate at which saturated air cools as it rises, considering latent heat release. Varies between 4-7 degrees C/km, average 6 degrees Celsius per kilometer. Types of atmospheric stability. 1. Absolutely stable atmosphere. Occurs when the ELR is less than the MELR. Any rising air parcel is cooler and denser than its surroundings, causing it to sink back to its original position. Example: temperature inversions, where a layer of warm air sits above cold air, preventing vertical mixing. 2. Absolutely unstable atmosphere. Occurs when ELR is greater than the DLR. A rising air parcel remains warmer and less dense than the surrounding air, causing it to continue rising. Example: hot surface conditions leading to cumulonimbus cloud formation and thunderstorms. 3. Conditionally unstable atmosphere. Occurs when ELR is between the MELR and DLR. Stable for dry air, unstable for saturated air. If an air parcel reaches the lifting condensation level, LCL, it condenses and becomes warmer than the surroundings, leading to instability. Example: development of large cloud systems like cumulus congestus and cumulonimbus. Effects of stability on weather. 1. Stable atmosphere suppresses convection, leading to clear skies, fog, and smog. 2. Unstable atmosphere promotes convection, resulting in cloud formation, thunderstorms, and turbulence. 3. Temperature inversions trap pollutants, creating haze and poor air quality in urban areas.
Here are 10 examples questions from atmospheric stability. Solve the question and comment your answer. 1. What is the primary factor that determines atmospheric stability? A. Humidity levels. B. Temperature lapse rate. C. Wind speed. D. Air pressure. 2. If the environmental lapse rate is greater than the dry adiabatic lapse rate, the atmosphere is A. Absolutely stable. B. Conditionally unstable. C. Absolutely unstable. D. Neutral. 3. What happens in a stable atmosphere? A. Air parcels return to their original position after being lifted. B. Air parcels rise indefinitely. C. Clouds develop rapidly. D. The environmental lapse rate is steeper than the adiabatic lapse rate. 4. Which condition results in the most unstable atmosphere? A. Cold air at the surface and warm air aloft. B. Warm air at the surface and cold air aloft. C. Uniform temperature throughout the atmosphere. D. An inversion layer. 5. What is the dry adiabatic lapse rate? A. 6 degrees Celsius per kilometer. B. 12 degrees Celsius per kilometer. C. 10 degrees Celsius per kilometer. D. 4 degrees Celsius per kilometer. 6. What atmospheric condition is associated with a temperature inversion? A. Enhanced convection and cloud formation. B. Increased thunderstorm activity. C. Rapid cooling of rising air. D. Stable conditions with suppressed convection. 7. The moist adiabatic lapse rate is lower than the dry adiabatic lapse rate because A. Higher atmospheric pressure. B. Latent heat release during condensation. C. Air molecules move faster. D. Increased humidity levels slow down rising air. 8. Which of the following atmospheric layers is generally the most stable? A. Stratosphere. B. Troposphere. C. Mesosphere. D. Thermosphere. 9. When does conditional instability occur? A. When the ELR is greater than the dry adiabatic lapse rate. B. When the ELR is less than the moist adiabatic lapse rate. C. When the environmental lapse rate is between the dry and moist adiabatic lapse rates. D. When the air is completely saturated at all levels. 10. What is the typical lapse rate in a temperature inversion? A. 10 degrees C a kilometer. B. 6 degrees C a kilometer. C. 0 degrees Celsius per kilometer. D. Positive lapse rate, temperature increases with height.